This videotape is for the beginning serviceman. We show and explain pulling principles. We show how to solve the 3 basic pulling problems using the correct puller tools. Pulling problems are presented, and then the selection of the correct puller is made. When pulling, you push on the center and pull on the outside. When installing, you pull on the center and push on the outside. The 3 basic pulling problems are: 1, pulling something off a shaft; 2, pulling something out of a hole; and 3, pulling a shaft out of something. The serviceman will have jobs that require pulling something off a shaft. This would include gears, bearings, wheels, and pulleys. Other jobs will require the serviceman to pull something out of a hole, such as oil seals, bearing races, retainers, and sleeves. Sometimes the serviceman may have to pull a shaft out of something, like a transmission shaft out of a housing, or a pinion shaft out of a housing. Now, let's look at some pulling problems that fall into these categories. Here we have 2 gears on a shaft. We want to pull the outer gear off. What puller should be used? We must choose the correct puller. The general purpose puller won't work because we don't have holes in the gear for bolts. The slide hammer puller does not have a wide enough spread for this size of gear. Also, this puller is too light. This small combination 2 or 3 jaw puller will do the job. This is the reach, or length, and this is the spread, or span. This is the forcing screw with a point that pushes the puller up. It fits a shaft center or a spacer. Different arrangements can be made by removing the ear bolts. Then the puller arms can be turned end for end with the small jaw as the gripping surface. The arms can also be turned over, changing the jaws to the outside for pulling on an inside diameter. The puller can be changed from a 2-jaw to a 3-jaw by moving one arm and attaching the third arm. The puller is installed by hooking the jaw gripping surfaces on the back of the gear. A spacer protects the end of a shaft from damage by the forcing screw. Put the spacer between the end of the shaft and the forcing screw. Turn the forcing screw until the gripping surfaces of the jaws are tight against the gear. Put a wrench on the square drive of the forcing screw and turn it clockwise. As the forcing screw is turned, the puller will pull the gear off. Here we have a pulley on a shaft. What puller should we use? The 2- or 3-jaw puller isn't correct because the edges of the pulley are tapered and the jaw gripping surfaces of the puller arms would slip off them. The bearing cup attachment won't work because it must grip on an inside diameter surface. This push puller will remove the pulley. Threading male-female adapters into the pulley gives a means of attaching the puller. Turn the legs into the adapters and put on the plate. To protect the threads on the end of the shaft, put in a step plate. This keeps the forcing screw from contacting the threads on the shaft. Then put on the cross block. Make sure the nut and ratchet wrench are under the cross block so that it will pull the pulley off. Put the extension handle on the ratchet wrench to provide the needed turning force. The forcing screw must be held from turning while the nut is turned with the ratchet wrench. As the nut is turned, it forces the cross block back, pulling the pulley off the shaft. A different arrangement can be made with the push puller to pull the pulley onto the shaft. Push the pulley on the shaft as far as it will go by hand. Use the threaded male-female adapter with the same threads as the crankshaft pulley bolt. Turn the puller adapter into the female part of the threaded adapter. Turn the male part of the threaded adapter into the hole in the end of the crankshaft. Put the forcing screw in the cross block with the nut on the top side. Turn the forcing screw into the puller adapter. The cross block must be centered to the legs and the nuts tight. Put the ratchet wrench on the nut. Hold the forcing screw with a wrench. Turn the nut with the ratchet wrench, and it will pull the pulley on the shaft. This bearing on a shaft presents a different problem and requires a different type of puller setup. The 2 or 3 jaw puller would only pull on the outer diameter and destroy the bearing, so it is not suitable. Of course, the bearing cup attachment can only grip on an inside diameter. The bearing pulling attachment has knife edges that will contact the inner bearing race. With the pulling attachment behind the bearing, turn the nuts on the bolts to reduce the spread and bring the blocks into position behind the bearing. The legs are in the threaded holes of the blocks and the plates, and the cross block and nuts are on. The nut on the forcing screw must be under the cross block. Be sure the ratchet wrench is on the nut before putting on the plates, cross block, and nuts. Put a spacer between the forcing screw and the end of the shaft to prevent damage. Force applied on the end of a shaft will distort and expand it. Put the extension handle on the ratchet wrench. Hold the forcing screw from turning with a wrench. We can now pull the bearing off the shaft. The bearing is now off the shaft, Tighten can be removed from the pulling attachment. Here we have a bearing cup to be pulled out of a hole. It must be gripped on the inside diameter, so we must use a bearing cup pulling attachment. This is the reach. This is the spread. The pull will not be great, so we can use the small cup attachment and the forcing screw from the general purpose puller to apply the force. A driver plate can be used to bridge the opening and push against. A spacer should be put on the driver plate to prevent the forcing screw from damaging it. Put the puller legs below the bearing cup. Turn the adjustment screw to bring the legs into position and tighten just enough to hold the legs stationary while the part is pulled. Unnecessary tightening can bend the legs as well as damage the inner surface of the housing. The forcing screw can be turned with a socket and ratchet. As the forcing screw is turned, the bearing cup attachment will pull the cup out of the hole. This problem requires a heavier bearing cup pulling attachment and push puller because of the force required. Turn the adjustment screw to retract the legs and put them under the bearing cup. Turn the adjustment screw to expand the legs just enough to hold them stationary under the cup. Don't over-tighten. Now the push puller can be attached to the bearing cup pulling attachment. The nut must be on the top side of the cross block. Turn the forcing screw into the puller adapter. Position the feet on the top of the housing. Tighten the nuts on the cross block so the legs won't move during pulling. So that it will be easier to hold and turn the nut, we will lay the puller down on the workbench. Hold the forcing screw with a wrench and use the adjustable wrench to turn the nut. The bearing cup has now been pulled out of the housing. This bearing can be pushed out using the general purpose puller. Bolts can be put through these holes in the housing and nuts screwed on the opposite side. A driver plate can be used to push against. A spacer can be put between the forcing screw and the driver plate. Put the cross block under the washers on the bolts. Turn the forcing screw with a socket and ratchet. As the forcing screw is turned, it will push the bearing out. This is a small bearing cup in a hole. The slide hammer puller can be used to remove it as there is nothing to push against. Put the jaws through the bearing cup. Turn the knurled cone to expand the jaws through the bearing cup. When the jaws are out against the cup, the slide hammer can be used. Hold the handle of the puller in one hand and move the slide hammer with the other. Be careful not to get your fingers in the path of the slide hammer. Several thrusts may be made to pull the bearing cup. Here we will demonstrate the use of hydraulic power to pull a bearing. A bearing pulling attachment is installed below the bearing. Threaded adapters are turned in the blocks to reduce the size down to the threads on the legs. The cross block with the hydraulic cylinder is attached to the legs. The maximum capacity of this puller is 17½ tons. A driver plate is put in the center of the housing to push against. A spacer is put on the driver plate to prevent damage to it. The forcing screw has now become the adjustment screw. It can be raised or lowered by turning the crank. The cylinder receives its hydraulic power from a pump. As the pump handle is moved up and down, the cylinder pushes the cross block up, pulling the bearing off. You have just seen some examples of the uses of pullers. the application and use of pullers is limited only by the imagination of the serviceman. Five statements on pullers follow. Fill in the blanks by supplying the missing word or words to complete the sentence. Pullers are sized by their blank and blank. Pullers are sized by their reach and spread. Pulling a gear off a shaft requires a blank force on the outer edges and a blank force on the center of the shaft. Pulling a gear off a shaft requires a pulling force on the outer edges and a pushing force on the center of the shaft. To pull a bearing cup from a blind hole, it must be gripped by the blank diameter. To pull a bearing cup from a blind hole, it must be gripped by the inside diameter. To exert a pushing force with a push puller, the forcing nut is installed on the blank of the cross block. To exert a pushing force with a push puller, the forcing nut is installed on the top of the cross block. A slide hammer puller is used when there is no surface to blank against. A slide hammer puller is used when there is no surface to push against. A pound-feet torque wrench is a common measuring tool you should be familiar with. Torque wrenches come in a number of sizes with different maximum torques. This is a small size. Its dial reads 150 pound-feet. This is a larger one, and it reads to 300 pound-feet. This large one reads up to 600 pound-feet. There is a movable rim on the dial. You can set the zero so it is exactly under the primary pointer. There is also a second follow pointer that you return to 0 by turning a knob in the center of the dial. Now apply a steady pull to the handle. You're applying torque through the drive end of the wrench. We stop when we reach 25 pound-feet, and the follow-up pointer remains at 25. We'll do this a second time so you can again see how the torque wrench operates. The follow-up pointer remains at 25. We can reset it to 0 for another try if we wish. What we're doing when we use a torque wrench is applying a specific torque to a bolt. We're actually stretching the bolt when we torque it. This is exaggerated, of course, but this is the concept that's involved in torquing. You have to be sure that you use the correct bolt. The bolt that's in the cutaway blind hole in the center of the picture is too long. You can't torque it without cracking the housing. The short bolt would be too short, and we would strip the threads before it would be torqued to specification. The correct bolt, of course, is the one that's called for in the parts book, or the original bolt if it is in good condition. Be sure it is clean and that the threads are not stripped or worn. For general torques and torque specifications, you can look in the service manual. There is a general section that gives the torques for standard bolts, nuts, and taper lock studs. Special torques are given in the specifications. There are pound-inch torque wrenches made for more delicate operations. This wrench is 12 times more sensitive than the pound-foot torque wrench. We're putting on an attachment called a crowfoot. We'll talk about this later because it changes the torque reading. Here we're using the crowfoot extension for tightening the lock nut on a pencil-type nozzle. Again, we center the 0 by turning the rim until the 0 is under the pointer. We turn the secondary pointer to 0. And we hold the adjustment screw with a wrench because we don't want it to turn. Then we tighten the lock nut to about 75 pound-inches. There is a certain tolerance on all torque readings. It is given in the service manual and usually is plus or minus a few pound-inches or pound-feet from the actual torque specified. If you didn't get a high enough reading the first time, you can torque the nut a second time. Let's talk about torque wrench extensions. The crowfoot that you saw previously did change our reading somewhat, so we should talk about torque wrench extensions and learn how to arrive at real torque. Let's look at another example. This is a standard torque wrench and socket. We have no problem tightening this main bearing bolt. But in this particular instance, there is an obstruction, so we can't get the socket on the bolt. What we have to do in this case, as we did with the crowfoot, is to put a special extension on the torque wrench so we can get the wrench into an otherwise inaccessible place where the standard socket and wrench would not fit. However, this extension adds 3 more inches to the length of the torque wrench. The length is calculated to the point where we have put white tape on the handle. There is actually a number stamped here telling you what the effective length from the drive to this mark is. In this case, it is 13 inches, measured from the drive to the white tape. The effective length is 13 and the total length with extension is 16. We use these figures as a fraction, 13/16. 13/16 of the desired torque of 140 is 114 pound-feet. There is another way of doing this, and it is with a simple calculator called a torque computer. The computer has a single slide with 4 bands. We find the effective length of 13 on the top line where the arrow has been put and have moved the slide so 16 is below it. The computer is set, and now you find 140 on the bottom band. Directly above it is 114, which will be the dial reading on the wrench for a real torque of 140 pound-feet. Let's actually torque a bolt to this specification. We put the torque wrench on a bearing bolt. We want 140 pound-feet of torque, but the dial reading should read only 114. This bolt is now torqued satisfactorily. Now let's look at the torque, turn, tighten procedure. Today some bolts are torqued first, then additionally tightened by this method. If we divide a circle into 6 parts, from 0 to here is 60 degrees, and from 0 to here is 120 degrees. From 0 to here is 180 degrees. Another 3 parts make a full circle of 360 degrees. A standard Caterpillar hex head bolt has 6 corners, 60 degrees apart. Here's a reproduction of the bolt head. If we lay it on the circle, we can see that the corners are 60 degrees apart. Let's put a mark on one corner of this bolt and start from the 0 reference line. Now let's turn it as we would in the torque, turn, tighten procedure. If we turn it so the second corner touches the 0 reference line, we have turned it 60 degrees. If we turn it so the next corner touches the 0 reference line, we have turned it 120 degrees. This is how you use the torque, turn, tighten procedure. After the bolt is tightened to original torque, make a reference mark on a stationary part and a matching mark on the bolt head. Now tighten the bolt. One corner passes the reference mark, so we've turned it 60 degrees. The second corner is 120 degrees. Torque multipliers come in different ratios. In the back is a 5-to-1 multiplier. It will give us an output torque which is 5 times greater than the input torque. The multiplier in front has a 4-to-1 ratio. Here is a socket in which you fit the drive end of a standard torque wrench. There's a gear train and a socket drive on the other side. This is an extra powerful torque multiplier with a planetary gear drive. It has a forward-reverse head attachment, which you see at the right. This multiplier has a high ratio of approximately 15-to-1. As you can see, an input of 35 pound-feet would produce an output of 500 pound-feet. Because of the enormous torque exerted, there is an overload feature to protect the multiplier. There is a shear groove in the drive shaft that allows it to fail at about 3,200 pound-feet. A replacement kit is stored in the handle of the multiplier. We'll now put a socket on a torque multiplier and show you how it is used. There's a pin in the shaft that must engage the socket. Now the torque wrench is attached. The handles of the wrench and multiplier will turn toward each other, and it will be impossible to hold the handle of the multiplier, so it must be put against a stop of some kind. With the 4-to-1 ratio multiplier, how much torque will be applied if the dial reads 100 pound-feet, 400 pound-feet? This is a special application torque multiplier. It is actually a double multiplier used for tightening the nut on the head end of a hydraulic cylinder rod. It has a combined ratio of 44-to-1. There is a special instruction available on the use of this tool. This concludes this presentation on torque multipliers. Remember to follow service manual specifications when torquing bolts. Select the correct wrench for the job. Don't overload or abuse torque wrenches. And use a torque multiplier for values beyond the range of the torque wrench. Torque wrenches should be calibrated periodically to ensure their accuracy. A 5-question quiz now follows. The question will appear on the screen, and the narrator will give the answer. If you do not want the answers to be given, turn down the volume of your television monitor. What is the reading on this torque wrench? The pointer reads 100 inch-pounds, or pound-inches, not pound-feet. What is the distance from the drive to the mark on the handle called? It is called the effective length of the torque wrench. What do you change when you add an extension to a torque wrench? You change the real torque by changing the effective length. How many degrees is it from one corner of a bolt to the next corner? With a hex head bolt, there are 60 degrees between corners. With a 4-to-1 torque multiplier, if the wrench reads 50 pound-feet, how much will the actual torque be? The torque will be 4 times greater, or 200 pound-feet.